get started. Oh, question already?
Yeah, I have a problem with the GIF. It says local changes would be overwritten by merge. Am I trying to pull it?
Yeah, so I would rename any files that you've created in the tree,
Okay.
and then they'll have different names, and it should be able to download the stuff with the old names, just fine. Okay, so this week we're going to continue talking about probability, in particular discrete probability distributions. That still applies. So just to review what we talked about last week a little bit, we defined a function for the probability of knocking down x out of n pins in bowling based on this logarithm function. And we used those probabilities to simulate R frames of bowling. And then we calculated many other probabilities that were implied by that using the simulations, which is not exactly, but it's the essence of the modern way of doing Bayesian computation, to just beat a problem to death with lots and lots of random numbers, but also using the rules of probability, what we refer to as the ancient way of doing the calculations, and they matched, indicating that the ancient calculations were describing the probabilistic properties of the model that we were simulating. And then we ended by using Bayes' rule to calculate the probability that 8 pins were knocked down on the first roll of a frame of bowling, given that 2 pins were knocked down on the second roll of that frame of bowling, which used Bayes' rule, but it wasn't really Bayesian because there were no unknowns. So pins are entirely observable. You could say, well, what if x1 is missing data or something like that? But there was nothing that was sort of fundamentally unobservable like beta in a regression, and we might ask the question, is this regression coefficient positive? And so the essence of being Bayesian is to use Bayes' rule to get the probability of what you don't know given what you do know. And so that would certainly include the essence of science, which is the probability of a hypothesis being true given the evidence. So what we're talking about in this class is certainly applicable to all of science, and especially applicable to social science. But you could also think about, okay, what's the probability of the future given the past? Which would certainly encompass all of business analytics for the most part, and probably a lot of other things. And so a huge number of questions can be put into the Bayesian framework. And then, kind of going back to what we were talking about in week 1, if this is applicable to essentially, everything that a QMSS student might want to do, why aren't we in a room that's 4 times this big? And, the answer to that question is that, not everybody is down for learning something like this. Even though what we did last week, what we will do this week is not, I would say, fundamentally hard, in the sense that we're only doing arithmetic. And anybody who can get into the QMSS program, and a lot of people who can't, can do arithmetic. But there is a lot to learn in terms of the vocabulary, in terms of like what gets multiplied by what, how it differs from other ways that you learned in other classes and things like that, that has to get learned. But it's not something that's unlearnable. It's just something that you have to decide you're going to commit to doing, to learning. Anyway, so if you make it through this, can source the bowling.r from the week 03 directory, and that's going to create four things that we did last week, but we're just going to pick up on. PR, this function on top here that we can evaluate for the probability of knocking down x out of n pins. Oh yes. I'll just tell you what my screen says. PR, which is the function to evaluate the probability of knocking down x out of n pins. Omega, which is an integer vector between 0 and 10, which is the sample space for bowling. Joint PR, which was this 11 by 11 table that we created last week, which has the probability of knocking down x1 pins on the first roll and x2 pins on the second roll of the same frame of bowling in the x1, x2 cell. And then we have frames, which was 10 million simulations of a frame of bowling. So that's a data frame or a tibble with two columns, one for x1, the other for x2. So does everybody remember those four things that we did last week? Okay. And also, we did them Tuesday at recitation. That video, if you haven't seen it, is up on Canvas under Panopto course video files or something like that. Okay, so next topic is expectations. So if we evaluate the probability over the entire sample space, we get these numbers, which we saw last week. They're the same. And then the question to be answered, what's the mode, the median, and the expectation for the first roll of a frame of bowling under this model? Let's start with the mode. What is that? Yes?
The most frequent number that occur.
Okay, so the element of the sample space with the highest probability, which in this case would be 10. Okay, good. What is the median number of pins knocked down on the first roll of a frame of bowling under this model? Eight point something?
Yeah, because we're looking for, whatever we have below 50%, above 50%, right?
Yes. So in this case, it being discrete, we can define the median as the smallest element of the sample space such that at least half the cumulative probability is less than or equal to that element, and consequently at most half is strictly greater than the element. So the median in this case is not 8 point something, but rather 8. Because, 28 and 16, that's 44. If we added another 11 to it, that would be greater than 0.5. So the smallest number such that at least half the probability is less than or equal to that element would be 8. So both the mode and the median are going to be elements of the sample space. Then the question is, what is the expectation for the first roll of a frame of bowling under this model?
Some product of those two things.
Yes. So the expectation of a discrete random variable is defined as the sum over the entire sample space. What are we summing? We're summing the element of the sample space times its probability of occurring. That sum is the expectation, and the expectation is so fundamental in probability it has its own Greek letter mu. So when you see me use mu, that is always going to indicate the expectation of a random variable, and so we can see the expectation as a probability weighted sum of a discrete sample space. In this case, the integers between 0 and 10. And so weighting each element of that sample space by the probability of its occurrence. And if you did that in this case, you'd get 7.0 something. Now, never in the history of bowling has 7.02 or whatever the expectation comes out to be pins been knocked over. So when the sample space is discrete, the expectation is still going to be a real number. So it's going to fall in the cracks of the sample space. So expectation doesn't really mean what it sounds like it means in English. Like there's an expectation that you pay your taxes or something like that. Something that is said, this is what should happen. Rather, expectation is given a specific technical meaning that you need to know. Namely, it's the sum over the entire sample space of the product between that element of the sample space and its probability of occurring, yielding a real number. Questions about any of that? A surprising and disturbing amount of confusion that you'll see out there is due to inability to even define these three terms, which are fundamental to working with probability, and the over-reliance on things like the normal distribution where these three numbers happen to coincide. But they're different concepts, even if in some cases they are the same number. And you need to know what concept each corresponds to. All right? Okay. So how would you use the R frames of bowling that we simulated last week to compute the expected number of pins knocked down on the first roll of a frame of bowling under our model? The modern way. So remember, frames is a tibble, 2 columns, x1 and x2, 10 million rows for all the times we simulated it. How would we compute the expectation of the first roll of a frame of bowling? Yes?
Would you just multiply each entry in that column by 1 over 10 million and then take the sum?
Yes, could do that, or more directly, you could just call the mean function on the x1 column, which does the same thing. Like I said, comes out about 7.04. And then how would you calculate it exactly? Using our function that outputs exact probabilities, deterministic probabilities. Yep,
So
good.
the sum of omega times PR of omega?
Indeed. Just like that, so it's actually a little bit above 7.04, but the modern way of doing it would have given us a perfectly acceptable answer in this case, or other cases in which this would be more complicated. Slightly more complicated, how would you calculate the expectation of the number of pins knocked down on the second roll of a frame of bowling? Exactly the ancient way, utilizing the 11 by 11 table we created last week called joint underscore PR. That has the joint probabilities of knocking down x1 and x2 pins on the same roll, same frame of bowling. Uh-huh. Yeah.
Is it the average of the marginal probability for the second roll, so our rows?
Average of the okay, so it does involve the marginal probability of the second roll, but it's not an average of the probabilities. What we're looking for is the expectation of the number of pins knocked down on the second roll. So if the way we did it the ancient way for the first roll is to take omega and multiply it by the probability of knocking down all that number of pins on the first roll and then summing it up. And now what we want to do is calculate the expectation for the second roll using the marginal probabilities. Yeah.
How about you create like a mutate function and you take like the score you had before with the peer and you just do like omega with like the remaining what's the name the remaining stuff in voting minus the first value you had with peer.
Okay, that sounded more complicated than the simplest way of arriving at the answer. So, first of all, how do we get the probability of knocking down some number of pins on the second roll of a frame of bowling from joint PR, our 11 by 11 table that we did last week at this time? Sum down the columns. Right, so the row pertains to the first roll, column pertains to the second roll. We need to sum the joint probabilities down the columns in order to get the marginal probability of knocking down x2 pins on the second roll of a frame of bowling, in which case the simplest way of computing this, which may or may not have been equivalent to whatever it was that you were saying, is to sum omega times the column sums of joint PR. Column sums of joint PR being the marginal probability of knocking down that number of pins on the second roll. Use those as weights for the sample space, get a number that comes out about 2. So this is the expectation of the second roll marginal. Had I used conditional probabilities, I would apply the same formula for calculating the expectation, but it would be a conditional expectation given whatever it is I'm conditioning on. So if we want, what's the expectation of the second roll given that 7 pins were knocked down on the first roll of the frame of bowling, then I would need to be using the conditional probabilities as weights when doing my expectation calculation. All right? Everybody clear on this? Good, considering there is a whole section in the reading about expectations. And they can also be used to calculate the expectation of a function. So let's say g of x is some function of a discrete random variable x. And let's remember that random variables are functions. So functions of functions are composite functions. Therefore, any function of a random variable is a random variable. Even if the g function here is deterministic, because it's a function of the random variable x, g is a random variable and hence may very well have an expectation. And the expectation of g is the sum over the entire sample space of x of g of x times the probability that x occurs. That is the expectation of g, but in general, that cannot be computed correctly by evaluating the g function at the expectation of x. In a special case where g is a linear function, that would be okay, but it is not true in general that the expectation of a function is equal to the function of it evaluated at the expectation. That is not true. So in general, you're going to have to apply that formula, and it works for any g function, but one way in particular that is useful is to make a decision that maximizes expected utility. Mentioned this a couple times without going into details about it until now. As a way that the Bayesian approach to probability ties very directly with decision theory as a way to how to proceed, how to make decisions as a result of doing some estimation thing to resolve the third source of uncertainty that we talked about on the first day. I've got the output of my model, now what do I do with it? Well, here's what you want to do with it if you're going to make a decision. First, someone, not necessarily you, but someone needs to enumerate D possible decisions that are under consideration. And someone, not necessarily you, needs to define a utility function, let's call it G, that depends on the decision being made, as well as possibly some other unknown or known quantities, such as X, the random variable that's unknown. Then you want to update your conditional probability distribution for all the unknowns, given all the knowns, using Bayes' rule. Evaluate, use those conditional probabilities that you get from Bayes' rule to evaluate the expectation of G for each of the D decisions, and then choose the decision that has the highest value in 4, thereby making the decision that maximizes expected utility. Now, in a business context, the utility function will often be profit. Or something like that. But in principle, it could be anything. So this is not super complicated, but you don't see it that often because people are, intimidated by step 3. How am I going to get the conditional probability of all the unknowns given the knowns using Bayes' rule? Well, that's what we're learning this semester. The other 4 parts are not super hard. I should also point out that frequentists, such as Fisher in particular, talked a lot of shit about this third step, using Bayes' rule to update your conditional probability beliefs about the unknowns given the knowns, because they said, okay, this is going to depend on the prior beliefs you have coming into it. It's subjective. It differs from one person to the next. All these sorts of things. But, and there's many reasons that you could say why that was, you could criticize that position. Let's make one short, simple observation right now. That the choice of the utility function, if you're going to use probability or quantitative analysis to actually make a decision as to how to, do something, well, the choice of the utility function is just as subjective. 2 different people could specify different utility functions depending on their risk preferences, and they might make different decisions even if they came in with the same prior beliefs about the unknowns, and even if they saw exactly the same data. This process might result in them making different decisions because they subjectively chose different utility functions that they felt were appropriate for them. So if the choice of the utility function inevitably is going to make this whole thing subjective, then why are we getting so caught up about the subjectivity of the prior? And if you're going to say, well, the choice of the utility function is subjective, like we shouldn't use it in science or public policy or running public companies or anything like that, then we don't have a way to make decisions as a result of doing our quantitative analysis. Alright? So if this is going to work, then we have to, tolerate some of the things that make some people squeamish about Bayes' rule. Alright? So that's how you could make decisions with it. Let's talk about the Bernoulli distribution. So Bernoulli distribution is defined over a sample space that consists of just 2 elements, 0 and 1, and it depends on a possibly and presumably unknown probability parameter pi that is defined on the 0 to 1 interval. So this pi has nothing to do with the circle. 3.1415. This is between 0 and 1. I'm just using it as a symbol. Has nothing to do with circles. And by introducing parameters such as pi, which like it starts with p, and so it reminds people it's a probability, we can make probability distributions more flexible and thus more applicable to a wide variety of situations in which we might want to be estimating pi. So, you know, if pi is low, if pi is high, its Bernoulli distribution is basically applicable anytime your outcome variable can be considered like success or failure. And, you know, we can estimate the probability of success. So the probability that x is 1 is pi. The probability x is 0 is thus 1 minus pi. Its probabilities have to sum to 1. And this can be written as a so-called probability mass function, a function that we can query to evaluate the probability of x for any element of x in the sample space. In this case, there's only 2. And these are often written, these probability mass functions, in terms of powers. Or you see ratios and stuff like that a lot. Pi raised to the power x times the quantity 1 minus pi raised to the power 1 minus x. And so if we have the probability mass function that we can evaluate to give us the probabilities, what is the expectation of x under a Bernoulli distribution? Did I catch a pi?
Yeah, pi times 1 plus 1 minus pi times 0. So
Uh,
pi total.
Right, so that is the right answer, and it was almost the right right explanation. So again, it's a sum over the entire sample space weighting by the probability of that. So we take 0, multiply it by this, putting in 0 for x, but 0 times anything is just going to be 0. And then we take 1 and then evaluate this at 1, so we get pi to the 1, which is 1, 1 minus pi to the 0, which is 1. And so this whole thing results in pi. So the expectation of a Bernoulli random variable is pi, and pi in general is going to be strictly between 0 and 1. So again, we have a situation, discrete sample space, expectation being a real number that falls in the cracks of the sample space. Did you have a question?
Yeah, what happens if we have like, if we know the value of x in this case?
So if you know the value of x, then x is not a random variable anymore.
Oh, yeah.
So the expectation would be like, you know, before you flip the coin, what is the expectation if we define heads as success? But we don't know if this is like a fair coin or whatever. Okay, that's good. Moving on to the binomial distribution. A binomial random variable can be defined as the sum of n independent Bernoulli random variables that all have the same probability of success, pi. So that leads to a couple of questions. What is the sample space for a binomial random variable? Let's start with that. 0 to n, or more specifically the integers between 0 and n. Yes, good. What is the expectation of a binomial random variable? Pi times n. So that seems like an intuitive answer. It's actually correct. So if we have independent Bernoulli random variables that all have the same expectation pi, and we have n of them, seems intuitive that the expectation would be n pi, and it actually is. Moreover, it can be proven, although we're not going to prove it right now, that the expectation of a sum is equal to the sum of the expectations. And that is true even if the random variables are not independent of each other. For most of the calculations that you do, You have to take into account whether the random variables are independent or not. But irrespective of that, the expectation of the sum is equal to the sum of the expectations, but that's sort of a rare special case. Okay, good, we got that. So what would be an expression for the probability mass function in the binomial distribution if n is 3? And as a large hint, there are 8 possible cases that we need to take into account of in our probability mass function, because the probability mass function needs to yield us the probability for everything that could possibly happen among 3 Bernoulli random variables with success probability pi. Yeah.
Alright, so we're gonna be a matrix n x with p power of x multiplied by 1 minus p with n minus x.
Yes, that is correct, and actually the simplest. Let's walk through the steps of that. So among the 8 cases, one case is all 3 Bernoulli random variables succeed. So the probability of that is pi cubed. Another case is that all 3 Bernoulli random variables fail, which is 1 minus pi cubed. So that gives us 2 cases. Then we could have 1 succeed and 2 fail. So pi raised to the power of 1, 1 minus pi raised to the power 2. But there's 3 different orderings that could involve 1 success and 2 failures. It could be success, failure, 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 success, failure, or failure, failure, success. So there's 3 different orderings of that same probability there. Similarly, could have 2 succeed and 1 failed, which would be pi squared times 1 minus pi to the first. That also has 3 ways of ordering it. So those are our 8 cases. And in general, we could write a probability mass function for the binomial distribution that encompasses all 8 of those cases and actually works irrespective of n. And choose x, that is the thing that looks like a fraction but without the horizontal bar there. And that function can be written as n factorial times n minus x quantity factorial divided by x factorial as well, of success probability raised to the number of successes times failure probability raised to the number of failures. And so this thing takes into account the fact that most of these are going to have multiple orderings in which they could occur, but that isn't important to us if we're thinking about the sum of Bernoulli random variables. Questions about that one? Okay. So this technically has 2 parameters in its distribution. N is usually known, but pi is often taken to be unknown and estimated, even though we're not really going to do that right now. But we can use this to calculate the probability of getting 4 strikes in a game of bowling. So a game of bowling consists of 10 frames. So how will we, first we need to add a game indicator to our 10 million tibble that has frames. So we just repeat 1 to 1,000,000. Each one of those gets to be 10. Then we have an indicator variable indicating which game the frame pertains to. And if we wanted to compute the probability of getting exactly 4 strikes in a game of bowling, which consists of 10 frames, how would we do that the modern way using the simulations we have from the model and this one line, which you should type. Anybody want to take a crack at answering this modern way? All right.
You just draw a bunch of random samples of 10 frames and then see how much of them have 4 strings in them.
Yeah, so we already have 10 million frames, and if we do that first line there, we can group them into 1 million games. So let's say we've got 1 million games of bowling, and then how do you propose to do what it is that you suggested?
I mean, can you just use you do a loop and just use the sample function, the sample 10 there over and over again, or?
Right, so we've already done the sampling, but we want to evaluate the properties of that. So can anybody help them out as to how you would go about doing that from what we have?
You can just group by this new variable.
Yeah.
And then summarize, yeah.
Okay, so we can group by according to the game. So we're going to do this calculation one chunk of 10 frames at a time. And we calculate a new variable that is true if and only if there are exactly 4 strikes in that game. So we can get it logical variable whether the x1 is equal to 10. Sum that up, see how many strikes we've gotten in this game. If that's exactly 4, then the variable 4 strikes will be true. And if it's anything besides 4, whether it's less or more, then that 4 strikes variable will be false. If we then ungroup, and so now we're dealing with these 1,000 values of 4 strikes, then we can simply compute the proportion of games in which this bowler, according to our model, got exactly 4 strikes, no more, no less, comes out to about 0.179 in this case. All right, so how would we calculate the probability of getting 4 strikes in a frame of bowling? Exactly using the probability mass function of the binomial distribution. That we just got through talking about. Somebody knew. How would we calculate this the ancient way? That we learned about 5 minutes ago. So it may not seem so ancient to you. Yeah?
Wouldn't it be like matrix of 10, 4, multiplied by p power of 4?
Do you want like in the arithmetic way or just like with pair programming stuff?
Either.
So yeah, my guess is that it would be like this matrix multiplied by p power of 4, multiplied by 1 minus p power of 10 minus 4.
Okay. And so how would you define P in the statement that you just made?
I would define p as the probability like for the strikes given a certain probability that I'm like the dominant player because we expect me of doing like 4 strikes. So the p value should be rather high, I guess.
Well, whether it's high or low, it's the probability of getting a strike on any one frame. and then we're gonna sum that up over the 10 frames. So in line of what was just said, 10 choose 4, because we have 10 frames in a game and we want to know the probability of getting exactly 4 strikes, times the probability of a strike raised to the power 4, times the probability of not getting a strike raised to the power 10 minus 4. That is the probability mass function that we talked about just on the previous slide, defining pi to be the probability of a strike under our model and evaluating this for x equal 4 and n equal 10 frames in a game of bowling. So you can certainly evaluate that. However, R already has the binomial probability mass function built into it and has the probability mass function for many well-known probability distributions. Those functions invariably start with D. So we could and have some suffix to them that has some number of letters that is in common with the name of the probability distribution, in this case, binom. So I don't know why they couldn't have just said D binomial, but they don't. The function is called D binom. It comes with R, so we can evaluate it at x equal 4 with size, which is the R's name of the argument for n, being 10, and the success probability being the probability of a strike, and we get literally same number there, similar to what we would have got in the modern way by doing this off the simulations, but slightly more precise. And this underscores the fact you shouldn't waste brain capacity memorizing probability mass functions. One, because they can always be looked up in books or Wikipedia or whatever if you need to know them. But moreover, if they're at all important, they're probably already built into R, in which case they'd probably do some tricks to make this more numerically accurate for like all sorts of different ranges of n and pi and whatnot that you haven't thought of. So it's preferable to use the R versions when they're available because they're probably more optimized in a variety of respects. But if those are available and they can easily be looked up on Wikipedia, there's no need to memorize formulas like this, or it's certainly not a priority. What is important to try to remember is, okay, what's a binomial random variable about? Okay, it's the sum of these Bernoulli random variables that are independent and have the same pi. Okay, what's a Bernoulli random variable about? Okay, it's success or failure. Just pi or 1 minus pi. Okay, then once you have sort of the summary of what a probability distribution means, you can use it, particularly if it has the necessary functions for doing so, already defined in R. We had to define our own function PR because bowling is not important enough to be included in R, so we had to make up our own. But for Bernoulli, well, not Bernoulli, because Bernoulli is a special case of binomial with size of 1. Binom, other things we'll talk about next and next week, those distributions are already going to be programmed into R for you, waiting to be used. And so you need to learn the things that are necessary in order to be like educated users of functions like this. All right. Questions about how to calculate the probability of 4 strikes in a game of bowling? Either the modern way or the ancient way? Yes?
When we're doing the 4 choose 10 in the easy version, that 10 is the number of frames in a game, not the number of men in a strike, right?
Right.
And then the 4 is the 4 success outcomes,
Yeah.
which is the strike in X1.
Yeah, so if we wanted, what's the probability of 3 strikes in a frame of bowling, we could evaluate either of these with 3 rather than 4, but n would still be 10. That's under the rules of bowling, basically 10 frames per game. So like I said, n is usually something that's like widely known. But pi might be something that needs to be estimated. Here we've just assumed a function for it, but we'll talk about estimating it as the semester goes along. Other questions? Okay. So, binomial distribution is fine, but it's a little bit limited in that it has an upper bound of n. And so oftentimes when we're dealing with count random variables, there's no explicit upper bound. Now maybe in practice, like, it shouldn't be that big, but there's nothing in like the rules or whatever that prescribes an upper bound for what n could be. And so people have asked the question, which may seem a little bit weird, what if n gets large, but pi gets small at exactly the same rate, such that n times pi, which we just got through saying was the expectation of a binomial random variable, remains constant, remains fixed, remains finite. So if we say, okay, what happens to the binomial PMF under that limiting process, recognizing that if mu is fixed, we can define pi to be mu over n. What is the limit of the binomial probability mass function given here if we substitute mu over n for pi? So let's just walk through that. You don't need to copy this down. And we just rearrange things a little bit with the n factorial in the numerator, and we've got an n to the x in the denominator. That's going to involve n x times in both the numerator and the denominator. So that one's going to go to 1, just leaving this piece left over, mu to the x divided by x factorial. And if we take the other piece, 1 minus pi raised to the power n minus x, substitute mu over n for pi, separate out these two terms here with 1 raised to the power n, the other raised to the power negative x. So this one is going to go to 1 minus 0 raised to the power something, so that's just going to be 1. This term over here might not be instantly recognizable to QMSS students, but if you were like math undergrad major, maybe, you might recognize this as one of many ways to define e raised to the power negative mu. So that's just like a fact that e raised to the power negative mu can be defined as the limit of this expression where mu over n is getting small, but you're raising it to the power n and it's getting big, balances itself out. So what we're left with is the probability mass function of x given mu with that term and e to the negative mu in it. So this business here, which is the probability mass function of the so-called Poisson distribution, which is defined for a sample space consisting of all non-negative integers. So it is a probability mass function over a infinite number but countably finite sample space consisting of 0 and all the positive integers. And so the Poisson distribution can be motivated the way we've motivated it here now as the limit of a binomial probability mass function under a particular set of limits. N getting large, success probability getting small, such that the expectation remains fixed. So n has to be going to infinity at exactly the same rate that pi is going to 0 in order to preserve that. If so, we get a new probability distribution that is appropriate for counts, possibly appropriate for counts, that don't have an explicit upper bound to them. but they do have an expectation mu that needs to be positive, but can either be large or small. And often would be unknown, in which case we would want to be estimating it. All right? So you don't need to really memorize the details of this, but you'll see this sort of thing a lot, where a long time ago people would say, okay, I have one probability distribution. How can I get another probability distribution by taking some limits to get, a simplified deal, something like that. So that's how the Poisson distribution can be defined, and that allows us to use it in a Bayesian way in the context of bowling, even though no one has done so, because this is a bit artificial, in the sense that I would usually consider parameters to be continuous, which we'll talk about next week. But this is a step beyond what we did last week toward what we'll do in future weeks that is mathematically valid and illustrates the mechanics of manipulating probabilities with a view toward using Bayes' rule, but isn't the way that any actual Bayesian would do this. But it is mathematically valid, and as such, again, provides intuition for how this sort of thing might be done in more complicated and certainly more interesting circumstances. So let's define a new probability mass function for the number of pins knocked down in bowling that introduces a parameter kappa that is a non-negative integer. And if you look at this expression, you might see that if kappa is 0, then the denominator is going to simplify, both of those. We get exactly the same probability mass function that we did last week. But if kappa is any integer greater than 0, this is going to be different. However, it can be shown that the probabilities still add up to 1 over the entire sample space omega. So if kappa is 0, we get these probabilities, which are the same probabilities that we got before, because this simplifies to the function we were using last week. But if kappa is 1, now the probability of a strike is only 0.21. And the probability of getting 9 has also been reduced. And the probability of 876 to 0 have increased slightly. And if kappa is 9, let's say, now the probability of a strike is a lot lower. The probability of 9 is lower, the probability of 8 is lower, and the probability of everything else is higher. So kappa is like a dial that we can turn, or it's like a dial that you could turn on like an old radio that like clicks when you turn it, because this is discrete. But depending on the value of kappa, you get different probabilities, but the probabilities still sum to 1 over the entire sample space omega. Consequently, we can use this for evaluating bowlers that may have different kappas governing their ability to knock down pins in a frame of bowling, which is similar but not exactly how we might approach this if we were doing it for real in the social sciences. So how could we use this function, which in week 3 has been defined to include a third argument for kappa in addition to n and x? How would you use that to calculate the expectation of the first roll if kappa is 2? So the conditional expectation for the number of pins knocked down on the first roll of a frame of bowling if kappa is 2. How would we compute that? Using the R, but the definition of conditional expectation.
Yeah. We do what we were doing before with our summarize over the row, but this time we're using the second row, the cap row.
So this is going to be what we're looking for here, an ancient calculation. Yeah, we could do this the modern way as well, but what we're looking for first is an ancient way of doing it, just one line.
So, I think exactly the same, but now we use, new probability, less.
Yes, the same, but different. So the sum of all the elements in the sample space multiplied by their respective probabilities, which are obtained by evaluating our function over all elements of the sample space omega when 10 pins are available to be knocked down, but now specifying the third argument to be kappa is 2, which is its non-default value. By default it's 0, so you would get the same probabilities as we had last week. But now we've generalized this to now have kappa be any non-negative integer, which affects the probabilities, and consequently the expected number of pins knocked down on the first roll of a frame of bowling, if kappa is 2, is only 6.345, in contrast to 7, or whatever it is we got earlier, when, for the expectation of the first roll of a frame of bowling, when kappa is 0. Alright. We use conditional probabilities, we get conditional expectations. The probabilities we were using before were still conditional. They were just conditional on kappa being 0. But kappa can be whatever we want, and whatever we might want to estimate if we were trying to estimate from data or something, bowlers' different kappas. So if kappa is unknown, how might we think about a prior on kappa? And you might say, I have no idea, I don't even know what kappa is. Like, if you'd asked me what that Greek letter was before, I wouldn't even known it was kappa. I mean, you should know the Greek letters, both the lowercase and the upper ones, but let's just put that aside for right now. How would you think about a prior on kappa? And so the way to do this in this case that works to some extent in a lot of other cases is to reason backwards from the expectation of an observable toward the parameters, and then maybe try to think about a distribution that you could use for the prior that is consistent with that. So what we have over here on the vertical axis is the conditional expectation for the number of pins knocked down on the first roll of a frame of bowling, given the values of kappa along the horizontal axis, even though those are in log scale. So as we saw before, if kappa is 0, then the expectation of the first roll is slightly above 7. If kappa is, 2, then the expectation of the first roll is between, it's 6.4 something, etc. And similarly for all integer values that are non-negative of kappa that we might want to evaluate this as. And we see immediately that there's a monotonic and in particular a decreasing relationship between the expectation of the number of pins knocked down on the first roll of a frame of bowling and kappa, meaning in a manner of speaking, we can interpret kappa as inability of the bowler. And for any bowler whose expectation for the number of pins knocked down on the first roll is between 5 and 7, we could find a value of kappa that is consistent with that. And so if you think to yourself, what expectation would you choose if you were bowling? using the Poisson distribution, which is the only one that we've talked about so far, that is applicable for a non-negative integer random variable, which is what we are treating for kappa. So if you think to yourself, well, how many pins could I personally average in the first roll of a frame of bowling, that gives you some value along the vertical axis. And you go over to like the nearest point on the curve and then down to the horizontal axis there. That would give you a way to choose the expectation in a Poisson prior over kappa. So somebody, where do you think you would personally fall on the vertical axis there? No, because 0 is possible. Okay, well, this particular setup is not going to accommodate like professional bowlers whose expectation would be well above 7. So like this would be more appropriate for grad student
Sorry, I thought you were
bowlers.
Yeah.
Oh, oh, so you were going to go kappa like here, so 5 and 5.6 or something like that. Okay, possible. Actually, anything is possible between 5 and 7 and has a corresponding value of kappa that you could set as your expectation in a Poisson prior on kappa. So usually we use the Poisson distribution for count data, but mathematically speaking, we can use it for a prior, and the math is exactly the same because one of the fundamental characteristics of Bayesian approach to quantitative methods in the sciences is that the way we use probability is exactly the same, whether we're talking about unknown parameters that are unobservable, like kappa, or data that is observable, like number of pins knocked down. We're going to treat the probability manipulations the same way, regardless of whether we're talking about something that's observable or not, which is what really set Fisher off. Because for him, kappa is not a random variable. It's unknown, but it's just some unknown constant. Bayesians come along and say, okay, I have my beliefs about kappa, and those beliefs are governed by the rules of probability, and I'm going to update and whatever. So it should be said, because it can't be said enough. Nobody ever said the Bayesian approach yields the wrong answer to the question that it asks. Nobody ever said, okay, here's this other non-Bayesian way of doing it that yields a better answer to the question that was asked. What Fisher is saying is that question should not be asked or answered, because it can't be answered objectively. The answer is going to depend in part on the prior, which treats kappa as a random variable, even though he says it should not be. And so this is going to be, to some extent, subjective. The answer that you get out at the end is going to depend in part on your beliefs about kappa coming in. So that's why Fisher says this question should not be answered. Fast forward many decades later, why do supervised learning people object to this? Well, they say, having to learn probability is hard, and they want to lower the barriers to entry for all sorts of people using, convoluted neural networks or whatever to predict stuff. We can make predictions without having to learn all this probability stuff, so learning probability isn't worth it, at least at the introductory level. Whereas Bayesians say no, got to use probability, got to learn how to use probability in order to quantify your uncertainty about your conclusions. So rather than saying, okay, like this is the prediction, no way of saying some uncertainty about it, we want to use probability, carry the uncertainty all the way through, even as we condition on data. So let's think for a second. Now I'll just show you how we would simulate R frames of bowling along with kappa, extending what we did last week. So you should type this in as I explain it to you. First, we're going to set R to some large number like 10 million, which is supposed to represent infinity, but it doesn't quite get there because can't do that on a finite computer. I'm going to set M equal to 8.5. The expectation in the Poisson prior on kappa. So let's say I thought my expectation, first one would be over here, and there comes out to be about 8.5 on the horizontal. So set R to be some huge integer, set M to be some positive number. Does not have to be an integer because this is our expectation for kappa under the Poisson prior. And then I'm going to use the following dplyr construction to create a tibble that has the results of R frames of bowling under our model, although our model has now been expanded to include kappa in it. So the first thing I'm going to do is draw kappa from its prior, which I said was Poisson, because that's the only probability distribution we've learned so far for an unbounded count. And I can do that using the built-in R function RPOIS, which again follows the convention for probability distributions. If you want to use the function for random number generation, that's going to start with R. If you want to use the function to evaluate the PMF, that's going to start with D. So I'm using RPOIS to draw capital R times from a Poisson distribution whose expectation is M, M being 8.5, what I said up above. So we're going to draw kappa from our Poisson prior distribution. You could use a different value of M. The steps here would be the same. I'm going to then pipe that to a group by statement because now I need to draw the first roll of each frame of bowling, but in so doing, I need to condition on the realization of kappa from the Poisson prior. Now, certainly a Poisson distribution is defined over all non-negative integers, but even if I do 10 million realizations, only a relatively small number of integers are going to be realized, and consequently I can do this more efficiently if I group the rows of my tibble, which currently just has kappa in it, by all the unique values of kappa that are realized, which is really not that much when 8.5 is used as the expectation. But to condition on the kappa draw, then I need to sample from omega however many times is necessary according to how many times that value of kappa came up with replacement because the pins get re-stacked up every frame, all 10 of them, using probabilities from evaluating my probability function over all values of the sample space omega when 10 pins are available to be knocked down, and using the realized value of kappa in that group to affect the probabilities. So different values of kappa yield different probabilities and hence different realizations of x1, that being the number of pins knocked down on that frame of bowling. And I can do that for all values of kappa to fill up my x1 column in this tibble of frames of bowling. I can then group by both kappa, the realized value of kappa, and the realized value of x1. which is going to be more groups, but it's still a very finite number of those. And I can do like we did last week to create x2 for the column of number of pins knocked down. And the second roll of frame of bowling with, replacement and whatnot, given that 10 minus x1 pins were available to be knocked down, and again conditioning on the realized value of kappa that was obtained in that frame by drawing from the Poisson prior. So if I then ungroup those to get a regular tibble, I now have a tibble that has 10 million or whatever R was rows, 3 columns, one for kappa, one for x1, one for x2. As you can see, the values of kappa can be any positive number, and in particular they can be greater than 10. But the number of pins knocked down in the first roll and the second roll are constrained by the rules of bowling. Combined, they have to be less than or equal to 10, and thus individually they also have to be less than or equal to 10. So are there any questions about what I did or how I did it? Let me just, before I get to questions, kind of situate what we did before. Last week, we just drew x1, and then conditional on x1, we drew x2, and we got a tibble with R rows that has that. And that allowed us to do, toward the end, what's the probability that 8 pins got knocked down in the first roll, given that 2 pins were knocked down on the second. And the reason why we did that, so kind of the first roll was kind of like the prior. It occurred before the second roll. And the second roll was kind of like data that we could condition on in order to get the probability of the unknown thing, which was x1, if like x1 was missing or something like that. And that was valid. It just seemed a little bit weird because like, why would you know x2 but not know x1? Like that would never really happen in bowling, like it's up on the screen or whatever. Now we're going a step beyond, a step more toward where we're going, and that we've introduced kappa, a fundamental unknown. So now we're sort of stepping one step back. Now kappa is prior to all this, so we draw it from its prior distribution, and then we draw data, both x1 and x2, conditional on the realization of kappa and the rules of bowling as well. And then, as we'll see in the next slides, we can go on to do more Bayesian stuff about inference about kappa, conditional on what we observe the results of bowling. So now we're sort of adding an additional step up front, which is draw kappa from its Poisson product. Okay, all that said, questions about any of this?
Could you explain why there's the first for the kappa and x1?
Right, so when we do this step here, okay, we draw 10 million values of kappa. That can all be done in one go. Some of those values of kappa are going to be 0. Some of them are going to be 1. Some of them are going to be 2, etc. But when we group by kappa, it basically makes a mini tibble. And it starts with the first value of kappa, which is 0. So it's going to do something different for those rows that all have the same value of kappa. 0 in this case. Now our function expects kappa to be a scalar. So rather than giving it like a vector that's just like 0, 0, 0, 0, 0, 0, 0, we just take the first element of kappa in that group of zeros and give that to our function, because the probabilities are going to be the same for all rows in the mini tibble where kappa was realized to be 0. So it's going to be the same 10 probabilities there, namely the ones we got last week. And then when kappa is 1, okay, there's going to be 10 probabilities, but these pertain to all the draws where kappa came up 1, etc. So this first business is just because our probability function expects scalars for n and kappa, even though you can give it a vector for x to evaluate the probability over the whole sample space, but good. Other questions? Got it? Okay. So how would we form the probability of kappa being something and x1 being something, conditional on m, conditional on 10 pins being available to be knocked down, under a Poisson prior on kappa? How would we do this the ancient way? What rule that we ostensibly learned last week would guide us to the answer for how we would form the joint probability of kappa being, 1 and the first roll of bowling being 7 or something like that, under a Poisson prior for kappa. Probability that kappa is 1 and x1 is 7, let's say. But the rule should work, and it does work if you learn it, for every value of kappa and x. How do we obtain the probability of two things being true simultaneously? Or more specifically, how did the ancients obtain such a probability? Yes?
And you multiply them.
Multiply what now?
The probability of kappa having a value and the probability of x1 having a value.
Right. Because the probability of x having any value is going to depend on kappa. So we'd be multiplying a marginal probability for kappa times a conditional probability for x given kappa. And that can be done like this. So again, kappa can be any non-negative integer, but on a computer you can't really go up to infinity, so I'm just going to go up to 999, which is practically infinite again. I'm going to use this outer function, but all this does is evaluate the prior, for every combination of between kappa of between 0 and 999, and every value of x and omega, it's going to multiply the Poisson probability mass function evaluated at k, which is one of the values of kappa. So dPois is the probability mass function in R for the Poisson distribution. M again is 8.5. So we evaluate that, the marginal probability of kappa, times the conditional probability of knocking down x pins on the first roll of a frame of bowling that has 10 pins available to be knocked down with that value of k. And this whole line here is going to produce a new two-dimensional table called joint PR. But this one is the joint probability between kappa and x1. Hence, it in this case is going to be 1,000. But you can think of 1,000 as being infinity or a finite approximation thereof, and 11 columns, one for each element of omega. So last week we had the joint probability between x1 and x2. Now we have the joint probabilities in a two-dimensional table between kappa being whatever and x in the column being whatever. And you can look at this if you do view of joint PR. I've only showed 8 rows here, but there's actually 1,000 of them. And there's 11 columns, which correspond to the elements of omega. These numbers are all real small. So the zeros that we have here in the first or second row, those aren't literally 0. They're just 0 to 3 decimal places. All of these are actually going to be positive numbers. But as you get, to other rows, you can see, okay, it starts to be, pop up to slightly larger probabilities of both these conditions being true, such as kappa being 7 and the first roll of a frame of bowling being 9. The joint probability of both of those happening is approximately 0.016, etc. And if you extend kappa out enough and you take the sum over this entire table, it's going to sum to 1, at least as far as a computer is concerned. Because the computer, like R, can only evaluate this stuff to like 16 decimal places anyway. So, if we do it, it's close enough to 1 for R to care about. Okay, so having done that, but actually going back to frames, what we created before, the tibble that has kappa, it has x1 and has x2. How could we utilize frames in the modern way to compute the probability of knocking down 8 pins on the first roll of a frame of bowling, given n equal 10, obviously, but irrespective of kappa, not conditional on kappa, marginalized over kappa, but doing it in a modern way by making a database-like query to frames, which has 10 million frames of bowling along with the realization of kappa in it. So how will we compute that probability of knocking down 8 pins on the first roll of a frame of bowling? Point of the modern way, in addition to being very general, which we'll come to appreciate more, is that once you've done the work to do all the simulations for your model, let's say 10 million, then the answer to the questions should be relatively easy, certainly easier than you all are making it out to be. And then you ought to be able to do a one or small number of lines query using the dplyr/database syntax to answer almost any question that you might really want to answer, such as what is the probability of knocking down 8 pins on the first roll of a frame of bowling, irrespective of kappa. Yeah.
We just use the previous code and like copy paste it and just change the regular x1 to assign it to 8.
Pretty much. We just need to take the average, which is to say the proportion of the logical vector is x1 equal to 8. The proportion of simulations where that is true is a very good estimate of that marginal probability. By not conditioning on kappa, we get a marginal probability rather than a conditional probability. So what I mean in the modern way is intended to make things easy is that we have relatively easy queries to our database of simulations to estimate anything we want, such as the probability that x1 is equal to 8. But how would you calculate this, or really any marginal probability for the first roll of a frame of bowling, using the awesome notation that I invented? So marginalizing over kappa, which is from joint PR, which is the table we created that's like 1,000 by 11 on the previous slide. But that is the probability marginalizing over kappa, which is not to be confused with the conditional probability setting kappa equal to 0. So this is conditional on kappa being 0. That's what we did last week. Now we want the probability of knocking down x1 pins irrespective of kappa, regardless of kappa. Marginalized over kappa. How would we do that the ancient way, using our 1,000 by 8 table of joint probabilities between kappa and x1? Sum those 1,000 values in the column marked 8, or any other column that we might want to know the marginal probability of. In this case, we get 0.1089, essentially the same answer that we got from our simulations. We could also get those, for any other value of x1, but this is marginalized over kappa. So it does not depend on kappa, but it does depend on m in our Poisson prior for kappa. But it's different from the conditional probability of knocking down x1 pins, given that kappa is 0, which is what we were looking at last week, which is why we need to know the difference between a conditional probability and a marginal probability, particularly when we have to do summation in order to marginalize over the thing that we don't want to condition on, which in this case is kappa. All right. People seeing the connection between this modern way of calculating that and the ancient way of calculating that, which is deterministic. Does not involve having to do 10 million simulations, but in a manner of speaking, does involve a bit more work to figure out what that would be. Got to know what rules to apply, etc. All right? Let's try it again. How would you compute the modern way, the probability that kappa is 3, given only that x1 is 8, using the 10 million frames of bowling that we simulated earlier today? Need everybody to be able to do this. It's the computational version of Bayes' rule. How to get the probability of something we don't know, given what we do know. So suppose you observe a bowler whose first roll they knock down 8 pins. How would you update your beliefs about what that bowler's kappa is? How do we get probability of what we don't know, given what we do know, the modern way? Yes?
So we filter frames on x1 is equal to 8, and then count basically like what portion of those things that have equal to 3.
Yes. I like it. Filter or group by imply conditioning. And then within that condition, what's the proportion of times something holds that's true or false? That gives us a probability. If we wanted conditional expectation, we'd filter on 8 and then take the average over kappa. All right? So this is what I mean by relatively simple database queries. And this not only is extraordinarily accurate, it is going to be extremely general. Whereas the ancient way, we'll soon see, runs into roadblocks. But in this case, we actually could calculate it the ancient way using our 1,000 by 11 table for joint PR. And how would we do that the ancient way? So last week, we calculated, you know, what's the probability of knocking down 8 pins on the first roll, given that 2 pins were knocked down on the second roll. We managed to do that, both the modern way and the ancient way. Now we're shifting one step back. What's the probability of kappa being 3, given that x1 is 8? But it's the same Bayes rule. Bayes only wrote one paper, and that came out after he was dead. But it was in the 1700s, and if somebody can figure out how to do this in the 1700s, you damn well need to figure out how to do it in 2023.
Is it the probability that k equals 3 times the joint probability of k of 3 and x1 equals 8 over probability x1 equals 8?
Yes, and the probability that x1 is equal to 8 is obtained by
Marginal probability of x1
yeah,
equals 8.
which is obtained by from joint PR. Sum down the column labeled 8. Yes. Joint probability of kappa being 3 and x1 being 8 together simultaneously. Those two things divided by the marginal probability of x1 being 8. Irrespective of kappa, that ratio is going to be between 0 and 1. Interpretable as the conditional probability that kappa is 3, given that x1 is 8. And it turns out to be the same number that we got the modern way from simulations. So Bayes' rule is correctly matching the properties of our model of bowling, where we have Poisson beliefs about kappa, and we might observe a data point such as x1 is equal to 8. Alrighty? Modern, ancient. It's pretty much only 2 ways to do it, and you're going to need to know both. Right now, some of you know neither, which won't cut it. But the ancient way certainly only involves arithmetic so far, and the modern way pretty much just involves some dplyr syntax after you get the simulations. So we got to learn how to do the simulations. But after that, it's learning how to make queries using the dplyr package, which you should honestly know how to do irrespective of this class. All right. So we can visualize, not just for kappa is 3. Wait, where'd my visualization go? Oh, I lost it. Hold on. Think about Bayes' rule, or simulations, or something pertaining to this class, while I regenerate my plot. Okay. So we can do the same thing to not just calculate the probability that kappa is 3 given that x is 8. We can calculate the probability that kappa is whatever given that x is 8. And I had a lot of slides here. And we can visualize it with a bar plot. So this is the modern way of doing it. We filter frames given the data that we observe. 8 pins get knocked down on the first roll of a frame of bowling, and then we put the proportion on the vertical and the value of kappa on the horizontal here, and we can see in each value of kappa what is the conditional probability of that value of kappa, given we observed in reality 8 pins got knocked down when this bowler rolled the first time. And those probabilities sum to 1. They're conditional probabilities given that x1 is equal to 8. But the probability of every value of kappa realized in frames which seems to be at most 26, even though kappa in theory could be any non-negative integer. So we can visualize this also. All right. Now, if we calculate the marginalized probability of a frame, first we get a crosstab of the 3 columns in frames, divide that by R so that things are in terms of proportions rather than counts. That is going to produce a 1000 by 11 by 11 array for kappa, x1, and x2. So giant contingency array there. And if we sum this over the second and third dimension, all 1000 values, we're going to get this 11 by 11 table here for the marginalized probability over kappa of a frame of bowling where x1 again is the row and x2 is again the column. So this is a table, 11 by 11, of the marginalized probability for everything that could happen on a frame of bowling under our model, but irrespective of kappa, because we've summed over all 1000 values of kappa underlying this. And here again we see, the probability of a strike, 0.01 or 0.133. Whereas conditional on kappa being 0, last week, this was like 0.28. But that was conditional on kappa being 0. But now our model is more general, more flexible, allows kappa to be any non-negative integer. And if we weight that by the probability, of the pins falling down, by every value of kappa and our prior distribution of beliefs, which was Poisson, then it's going to be putting weight on kappa is 1, kappa is 2, kappa is 3, kappa is 42, all these. And since higher values of kappa are associated with worse results in bowling, the probability of a strike marginalized over kappa goes down. And you get the other numbers here, which are going to add up to 1 for a frame of bowling, but irrespective of kappa. Okay, let's pick it up a little bit now that we've had some more practice. How would you compute the modern way the probability that kappa is 3, given that m is 8.5, x1 is 8, and x2 is 2, using our 10 million frames of bowling that we simulated? That we already simulated. So all we need to do at this point is make the proper database query to evaluate this conditional probability. What would that database query be?
Just use the additional condition. Still use filter, but use additional condition that x2 equals 2.
Yes. The m equal 8.5 is already baked into the prior. That's a constant. So there's no need to filter based on that. But filter on x1 being 8 and x2 being 2 simultaneously. Now we get the frames that we're talking about, but there's going to be a bunch of those. And then among those subset, we can calculate the proportion where kappa is 3. It comes out to be 0.0244. A small number, but kappa in principle could be any non-negative integer. So it's not surprising that the probability of it being any one integer like 3 is not a huge number. Well, it's got to be between 0 and 1. This is the probability, conditional probability. But it's pretty close to 0. But not so close to 0. It's 0.0244. So how would we calculate that same probability exactly utilizing marginal PR, which we just created, this 11 by 11 table for the probability of what could happen in a frame of bowling, irrespective of kappa? We can do this. We can do this. Yes?
If we use the do like imaginary PR with 3/8. I'm not sure, but 3/8 divided by the sum of imaginary PR. No, that's not.
That what you meant? Because that's the right answer.
Okay.
Poisson probability of 3, given the expectation of m can be 8.5, whatever, times the conditional probability of knocking down 8 pins on the first roll of a frame of bowling, given that kappa is 3, times the conditional probability of knocking down 2 pins on the second roll of a frame of bowling, given that 2 pins were available to be knocked down and that kappa is 3, all divided by the marginal probability of knocking down 8 pins on the first roll and 2 pins on the second roll, irrespective of kappa. It's Bayes' rule, ancient way, conditioning on both x1 equal 8 and x2 equal 2. And it's the same number rounded to 3 digits that we obtain in the modern way by making a database-like query to our 10 million simulated frames of bowling. So these two ways of doing it are both describing the same thing. Our model for bowling, which has now been generalized to introduce this kappa inability parameter for the bowler or bowlers in question. All right. So we got this number 0.024177771. Now suppose we calculate the posterior probability for each value of kappa given only that m is equal to 8.5 and x1 is 8, and use that as our prior probability mass function when subsequently conditioning in the second step on the fact that x2 equals 2 in the first frame of bowling. So we can form a prior probability mass function, which is really a posterior probability mass function, by taking all the rows where the joint PR is equal in the 8th label column and then normalizing it out by the sum in the 8th label. We define a likelihood function, so this is going to be a function of kappa evaluated only at x equal 2 when there are 2 pins available to be knocked down. We take the prior function, multiply by the likelihood function to get the numerator of Bayes' rule, and to get the denominator of Bayes' rule we just need to sum for all possible values of the numerator. And then we can evaluate the ratio of the numerator and the denominator when the numerator corresponds to the kappa value of 3, and we get 0.024177771, which is literally the same answer that we got before when we conditioned on 8 pins getting knocked down on the first roll and 2 pins being knocked down on the second roll simultaneously. And that is no accident. We end up with the same posterior probability for kappa being 3 as we did before when we used a Poisson prior for kappa, and then with m equal 8.5 expectation, and then conditioning on both 8 in the first roll, 2 in the second roll simultaneously. So in a manner of speaking, before we arrived at this posterior probability in one big step where we conditioned on a whole frame, but we could and did get the same posterior probability when we do this in 2 steps. Start with a Poisson prior on kappa, update it once, conditional on x1 pins being knocked down in the first roll of a frame of bowling, and use that first posterior probability mass function, conditional on x1 being 8, as our prior on kappa to be updated in the second step by conditioning on x1 being 2 in the second roll of our frame of bowling, and if we do the calculations correctly, we get the same answer, which might not be so much of a surprise if we see, okay, well, we're just really doing multiplication and division here. Both of those are associative, so we can group the terms however we might want, and we should be getting the same answer, and we do. And so, as I've been emphasizing, Bayesian inference is a system of belief management, and a minimal requirement of any system of belief management is that it should be coherent, even given just one data point, or even 0 data points. It's still coherent. Your beliefs about kappa are just those reflected by your prior distribution. But it should be coherent, should be updatable, even if we just get one piece of information to condition on. If you have 2 data points, let's say in one frame, that's 1 data point twice. If you've got n data points, that's 1 data point n times. You can update your beliefs n times, and you'll get the same thing as if you updated your beliefs just once using all n data points simultaneously. And other quantitative methods are not belief management systems. They don't have that coherence. They don't even work if you only have 1 data point. Like, try random forest with 1 data point. Your computer will melt down. Like, how would you even decide whether to put it into training or testing? Like, it's just not built that way. But Bayesian approach is built from the ground up. It should work if you just have 1 data point, and if you have n data points, that's just 1 data point n times. And as a result, we can build a coherent system of inference around it. But it takes time, which we're out of today. I will post the first homework tonight. It'll be due before class next week, so you have a week to do it. It'll cover, what we've done so far. We'll have a recitation section on Tuesday at 12:10, either on Zoom or in IAB 27DB if you want to show up in person. And we'll have office hours Tuesday afternoon that you can sign up using the link on the syllabus. And I will be answering questions on ed discussions, which almost all of you need to be asking more of, because that's an important part of your participation grade, and it's an important part for clearing up any misunderstandings that you might have, which are understandable because this is new material, but what's not understandable is, not asking about what you don't know. Because we've been doing the same things for 2.5 weeks now. Slight changes, making them better, but we've been doing the same thing, modern, ancient, over and over. So if you have questions about that, need to be asking them. Yes?
Do you count a response to a question as fulfilling that criteria?
If it's a correct response, yes. Yeah.
I saw that you were putting negative participation, you were asking like 1 question, so you got the hour. Is that true?
Only online counts, but you're welcome to come.